I'm going to show you how to make your own PCBs at home using just two materials. If you've never made a PCB before, this video will give you a complete starting point. If you've been building electronic projects for a while, you've probably used breadboards in almost everything you've made. Breadboards are excellent for prototyping because they allow you to build and modify circuits quickly without soldering. You can try ideas, fix wire mistakes, and change components in seconds. For learning and testing, they are hard to beat. However, as soon as you want your project to last longer, the breadboard becomes a limitation. The circuit is physically large, the connections are unreliable, and even a small movement can break contact between components. Breadboards are not designed to survive vibration, transportation, or long-term use. At that point, if you want a circuit that feels solid and professional, you need a more robust solution. The next step that many people take is using a universal board or perfect board. This allows you to solder components instead of just plugging them in. While this improves mechanical strength, it introduces a different problem. Wire becomes messy very quickly. Large circuits are difficult to debug, and the final result usually looks improvised rather than designed. It works, but it is not elegant. This is where a printed circuit board becomes important. A printed circuit board does two fundamental things. First, it mechanically secures every component in place, preventing movement and ensuring that connections remain stable over time. Second, it provides electrical connections through copper traces that are fixed exactly where you intended them to be. Instead of wires flying across the board, current flows along well-designed paths with predictable electrical behavior. When you look inside any modern electronic device, everything is built on PCBs. Phones, computers, industrial controllers, and medical devices all rely on printed boards. However, modern manufacturing makes PCBs look much more complicated than they actually are. Multi-layer boards and surface-mount parts give the impression that PCB manufacturing is inaccessible to hobbyists. In reality, the basic principle behind PCB fabrication is extremely simple. Protect the copper you want to keep and remove the rest. That is exactly what we will do in this video. To demonstrate how accessible PCB manufacturing really is, I limited this entire process to only two core materials: copper-clad laminate and ferric chloride. No CNC machines, no UV exposure boxes, and no expensive chemicals. Everything in this video can be done on a small desk with simple tools. The goal is not to create factory quality boards, but to build real, functional PCBs that you can use in your projects. Copper-clad laminate is a board made of fiberglass or resin with a thin layer of copper on one or both sides. This copper layer will become your electrical traces. Ferric chloride is a chemical additive that reacts with copper and dissolves it. But by selectively protecting certain areas, we can control exactly where copper remains, and this will be the traces that connects the electronic components. Before proceeding, it's extremely important to understand that ferric chloride is not a harmless substance. It stains surfaces, corrodes metal, irritates skin, and can cause serious eye damage. You must use gloves, eye protection, and good ventilation. Never store it in metal containers or never pour it into a drain. Dispose of it properly according to local chemical disposal guidelines. Safety is not optional here. For the first project, we are intentionally keeping the circuit simple. The purpose of this exercise is not electrical complexity, but understanding the PCB process itself. The circuit consists of a single LED, a current limiting resistor, and a battery connection. First, clean the copper surface using a dry cloth or a steam wool to remove any dirt. Once the board is clean, use a permanent marker to draw the traces directly onto the copper. The ink from the marker acts as a resist, preventing ferric chloride from reaching the copper underneath. This method works surprisingly well for simple circuits. With the board prepared, place it on a plastic container filled with diluted ferric chloride. If you bought ferric chloride in powder form, mix 1 part chemical with 2 parts water by mass. For example, if you use 1 ounce of chemical, which is about 28 grams, add 2 ounces of water, or 56 grams. Gently move the container every few minutes to help circulate the solution. One tip: the copper should be facing downward in the container so the active material does not settle on the board. After some minutes, the exposed copper will be removed. Once etching is complete, clean the board again with water and remove the marker ink using alcohol or a similar solvent. What remains are copper traces exactly where they would draw. At this point, drill the holes and solder the components into the right place. Then it's time to test the board. As you can see, the LED works the way we wanted, confirming that the PCB process was successful. The first project was too simple, so now we are gonna make something cooler. For the next project, I built the circuit on a breadboard first to verify if it works. Two LEDs blink alternately when power is applied. This is not a random behavior, it's a result of a flip-flop circuit. A flip-flop is one of the most fundamental circuits in digital electronics. It's a bistable system, meaning it has two stable states. Once it enters one state, it will remain there until an input causes it to change. Each flip-flop stores exactly one bit of information. All digital memory systems, whether in old computers or modern processors, are ultimately composed of massive networks of such circuits. In this design, two transistors, capacitors, and resistors form a simple oscillating flip-flop. Each transistor alternately turns the other off and on, creating the blinking effect. While this may appear simple, the same logic forms the basis of clocks, counters, and memory registers. To create this project, you need two BC547 transistors, two LEDs, two 100 microfarad electrolytic capacitors, two 10 kΩ resistors, and two 2 kΩ resistors. I designed this circuit using KiCad, a free and professional grade PCB design tool. First, the schematic is created, then it's converted into a board layout where the components are arranged and the traces are routed. Once the design is complete, I started drawing it on the copper. Then I went to manufacture it, but the first PCB didn't work quite well. Some traces were faulty, so I decided to create another PCB. After some time and hard work, I finally got a PCB suitable for the project. I cleaned it, drilled the holes, and soldered the components according to the schematic appearing on your screen. Then connect the battery and watch the LEDs blinking one after the other. Really cool, right? Drawing traces by hand works well for simple designs, but fail when circuits become more complex. As the number of components increases, the likelihood of mistakes increases as well. Spacing becomes difficult to control, routing becomes inaccurate, and the consistency drops. For more advanced projects, I would recommend you use PCB manufacturing services. Today you learned not just how PCBs are made, but why they matter. Even with minimal tools and inexpensive materials, it's possible to manufacture functional boards at home. If you want to take electronics seriously, PCB fabrication is not optional knowledge. It's a fundamental skill that opens the door to better design and professional level projects. If you found this video useful, consider subscribing for more future tutorials. And before the next one comes out, check out the video appearing on your screen right now to continue this learning path.